Presentation is by our chairman, Aleksey Marchenko, titled Thermo-mechanical Loads of Sea Ice on Surface. 1 hour, please.
Yeah. So I built up my presentation in three portions. So the first portion I will give just information known from the literature, and second part I will describe 3 examples of such type interaction observed in Spitsbergen, and the biggest part, last part, is just analysis of that interaction. So then the information about ice structure interaction you may find, for example, in book of Sanderson, and he said that there is 2 types of interaction when temperature is changed. So then ice expand and may produce loads on the construction if ice is confined inside the construction. And the second part of interaction is when ice is partially confined between local structure and, for example, shoreline. So in that case, ice thermal expansion will influence load on the structure. So then he also mentioned that, of course, thermal load could be big, but there is a time to penetrate temperature inside the ice due to the heat transfer, and this time is not short. And for example, to get to 1.5 meter depth, we need almost 100 days. So therefore, weather changes may influence ice temperature, but not very deep. So then, if you go for deformation of ice, so then if temperature penetrate deeply into the ice over some time, so then the creep could be important, and therefore thermal loads are significant only when temperature change suddenly. And if temperature change slowly, so then thermal loads are reduced due to the stress relaxation. And in this simple model, which is formulated for thermal loads, where thermal loads are in balance with elastic stresses and creep stresses with representative constant and power law with n equal to 3. So you see that if representative time, like say 10 hours, so then if you have significant change of temperature of few degrees, so then creep is very important. If it is just 1 Kelvin degree, so then creep is not so much, but still could be should be taken into account. So therefore, we have combination of thermal coefficient of thermal expansion, combination of creep, and the combination of temperature diffusion. So then, what we have on practice in Spitsbergen? What example? So here you see floating pier, and it should survive for over winter time, and in summer time it is used. So now it is much bigger. We don't have ice last years, but still it was 2010. So what we have in winter time, and what was not accounted in the book of Sanderson, so that is tidal variation of water level. Tidal variation of water level influence hinge zone, formation of hinge zone between ice foot, which is frozen to the shore, and ice which is moving up and down. And inside hinge zone we have system of cracks, and the water penetrates through this crack, freeze inside between the cracks, and push structure onshore, offshore. So then, for example, 2011 gangway was cut to avoid significant damage with power cable. So another example of combined action of tidal elevation, water level, and this ice creep offshore. So you can see here there are 2 pipes. I installed these pipes with thermistor string inside, I wanted just to compare temperature. In one pipe was closed at the bottom, another not closed. Just want to measure temperature. And one pipe at the edge of this bridge, so that is small bay, small boat harbor, and here we have this bridge, and one pipe get into the gap between floating ice and the wall, and this pipe survived. And another pipe was broken in 2 weeks. So then ice was a little bit creeping, at the same time moving up and down. That influence bent, then pipe was broken. So example which I'm going to discuss today is related to coal boat harbor in Kapp Amsterdam, in Svea. So then here you see the moment of construction. It is in 2000. So length of this quay is 195 meters, and it is standing on vertical pipe with 80 centimeters diameter, and pipe are filled with concrete and going into the sea bottom on 30 meters. And some of pipe are connected by sheet piling. I call it cofferdam, and the soil was this cofferdam were filled with soil. So then the depth of water inside cofferdam is 5 meters, and outside is 15. So that is like big columns. So then we discovered significant deformations of these cofferdam walls. This displacement was about 1 meter, so that is from laser scanning. So in winter time, this quay is not used, and ice is formed in the sea, and ice is formed inside the cofferdam. So then you see figure how it looks when we have low tide. Then you see how it looks when we have high tide. So then tide, the water, seawater penetrate through the ice, and places where it penetrates sometimes visible, sometimes not. So the thickness of the ice inside cofferdam is 2-3 meters. Thickness of ice in the sea is always less than 80 centimeters. So, and this big thickness is explained by this migration of water which freeze on the surface and not only on the bottom. So then this schematic what we have in low tide, we have this ice confined as hanging. In high tide we have water on the surface, and this depth can reach 15-20 centimeters. So structure of ice. So we have very granular ice with small grains below the quay, and this is a horizontal section of ice in floating ice in the sea. So we observed significant variation of salinity from the low water to high water. So then when water level is going up, we have the increase of salinity, ice salinity. So I want to show so if we drill through the ice, we did it once, so then we have this situation. So this is hole drilled through the ice with a auger, so and we got water coming and coming, so then it never stopped. That's what we have. If we don't drill, so then it is coming, but not with this fountain. So then we decided to investigate stresses performed by ice on the walls of cofferdam, because initially we were not sure that it came from the ice. So maybe these deformations were related to soil actions, because we have inside a big amount of soil. So then we deployed these load cells on the walls of cofferdam. So this wall, which has significant deformation, and this seaside wall. So here we screw this load cells to P-shaped beam, and then we brought this beam and screw it to the sheet piling. So then you see configuration that we wanted to have these loads below the water level. So therefore we need to screw that with bolts to sheet piling, and most important thing was to fix this bottom bolt, because it was only possible to do when we have lowest tide, and lowest tide is in November, completely dark time. So then we had around half an hour to drill with hand drill through the wall from plastic boat inside the key. So then that was a moment right time when we fixed upper bolts, but then bottom bolts, it was more difficult. So then we got data. So and 2013 and 2015. 2014 was warm winter, we didn't have ice loads, and 2016 as well. So we got records over 2 winters, and you see that maximal loads, so that is some occasional load, but maximal pressure we registered up to half of megapascal, and these loads are oscillating. I will show with more details, and important to see that biggest loads were observed when air temperature was above -10. So in relatively warm weather in the end of season. So then here you see, I forgot to tell that in addition to these load cells, we installed thermistor string, which measure temperature inside, that was in thin pipe, and from inner side of this pipe, of this pile. So then each 20 centimeters. In addition, we have thermistor string together with these load cells, but they are on some distance from this concrete load cells, but we analyze both of temperatures. So then there is example of temperature profile. So temperature profile more or less stable, and we have in the water freezing point around -2, then we have some profile, and in the air we have air temperature. But around this mean profile we have temperature oscillations. And these temperature oscillations, of course, in the air, they follow air temperature oscillations, but in this spot they have a semi-diurnal period according to tide. And below in the water, of course, we don't have temperature oscillations. So, and if we compare load, so this load cell 3, load cell 3 is that, and 4 is deeper. So then in this year, for example, here you see this situation. So then load cell 3 has highest loads, and highest loads reach with lowest temperature. So, but in some points it can associate with highest temperature. So there is we didn't observe always synchronization with temperature increase and increase of the load. Sometimes it doesn't, sometimes not. So then next record from 2015, again in this year we also performed records of tide in the same place. So then we see that biggest loads were observed when we have biggest tide. And biggest load mostly observed on the cofferdam wall with most significant deformations. And also they were observed after this time when air temperature is not coldest, but maybe ice was thicker here. We didn't measure continuously ice inside cofferdam, because when ice begin to form, so there is no solid ice inside. It is always broken, but starting from some point, it became solid. So then you see that there is some shift. So black line show tight, and blue line show lots on lot cell 4, that is on lower level. So there is some phase shift, but between tight and maximal lot, but good synchronization between temperature and maximal lot in 2015. So in 2013, again repeat, so then we didn't observe always synchronization. But then temperature oscillations. So this, it is about 5 degrees. It is recorded temperature lot cell 3, lot cell 2. And temperature oscillations recorded on thermistor string, they are smaller. So therefore, this amplitude of temperature oscillations is not the same over the entire cofferdam. The size of cofferdam, it is in the length along shore, it is I think 40 meters, and in the direction to the shore, between two pipe distance 10 meters, and then ice is, if you go back, so this distance is 10 meters, and this distance is 20 meters, but here ice is laying on shore, so therefore when temperature changes, so then it may expand here. So therefore maximal loads observed on these walls, on Z. So then here you see semidiurnal oscillations. They are quite visible in 2015 as well. So sometimes highest loads observed when we had synchronization between air temperature and temperature induced by tide. So then in that case we had these events. So and no temperature oscillation is in the water. That is very stable. So then we also deployed some sensor in the middle of the cofferdam to compare stresses measured in the walls and in the middle, and we also installed for several days this camera reconics, making video each 15 minutes. So then I want to show you this example. So the ice little bit displaced. There is daytime variation, but the tide amplitude is changing because of moon phase. So and then on certain time we have water coming. So the weather is changing. Yeah. So the water appears not always, but when tide is big, so then we always have water. And tidal variation of water level is changing from 1 meter to 2 meters. So, but this but in addition, so that is recorded tide. In addition, we have that mean water level is also changing. So then tide is changing around mean water level, but mean water level is changing because of other constituents of tides. So therefore, process is not just pure periodic. But of course, we made a hole in central part of this coffer dam, and that hole was filled with water. So maybe we influence processes inside, drilling this hole, not through, but where we freeze the sensors. So, but still, inside the hole, temperature variations were much smaller, and the ice was wet inside. So, but then here you see temperature variations inside the ice. They have semi-diurnal period. And temperature variation on the surface, they have diurnal period because of the daylight and night. So, and we have variations of pressure with some shift from maximal tide in the central part of the coffer dam and recorded on the walls. So on this picture, I calculated the duration of flood period when tide water is high, so then I marked it with red. So then it has some dependence from, so tidal amplitude was changing and flood time also was changing, but also we observe something here, from small tide we observe flood. So then I cannot explain that, but in general, of course, flood time increase with increasing of tidal amplitude. So then, of course, water can penetrate through some cracks. It is difficult to imagine that there are big cracks in 3 meter thick ice or 2 meter thick ice which is compressed and in cold weather. But still, so therefore, to be sure that we observe migration through solid ice, we organize experiment in the lab. So then we have a tank that is 1 meter, that's 1/2 meter, so you see sizes here, and we place inside the tank air balloon, create ice at the surface, then pump air in the balloon and measure it. Deformations of ice and deformations of wall with fiber optic sensors. So temperature in the room was -10. So then here we have thermistor ring, and this is strain sensor, and here we have strain sensor. So then temperature profile was just linear, but around the temperature profile we have some variation. So then here you see results. So that's increase of pressure in the tank. And then we observe tank wall strain, negative. It is shrinking because the wall were damped inside, from inside to outside. And ice expanding. This yellow curve, so that is expansion of ice. So, and at the same time, we observe increase of temperature inside ice, and zero show room temperature. So room temperature was decreasing because of some reasons. That is how these fans work. But even if room temperature decreases, so the temperature inside ice increases. So then, with this experiment, we assure that pressure gradient over the ice contribute with brine migration through the ice. So I want to again to show you couple of videos like visualization of this brine migration. So then here, this video, you see, this is solid ice, -10. you see, this is brine coming through the ice with thickness 10 centimeters. It is solid ice. I took sample from that place after the experiment. That was solid ice. So, if we drop pressure below the ice, so then we observe that ice surface is dry. So then this brine is sucking by water and going downward. And if we look from below on the ice, then we don't see initially nothing, but after some times the air is coming through the ice inside the tank. So you see many air bubbles. So then, therefore, my vision of the process observed inside the cofferdam is shown here. So sea level is changing, and the ice is fixed. It is little bit movable, but it is not floating. It is confined. So then, this ice inside cofferdam include closed brine volumes and channels, brine channels. And these channels may have different concentration. In some places, we may have high concentration of channels going through the ice, and in these places, we observe these rings. In other places, concentration of channel is different. So therefore, filtration velocity is not the same. And for the process of thermal expansion, is important not rare regions with high filtration velocity are important, but regions which have some mean characteristics of filtration. So the model of this effect was elaborated based on Darcy law, and we need to include in Darcy law permeability of this ice. So then we integrate just this through the ice thickness. We have finally this equation, and this term with theta function is responsible for the process that when water level is above the ice, so then we have here hydrostatic pressure, and pressure at the bottom is changing according to sinusoidal law. But we need to place in the model mean water level with respect to ice bottom. So then we don't know it, but it is tuning parameter. So then we introduce dimensionless variables, and we run model, and it shows reasonable values when ice permeability is about 10 in minus 10 square meters. So it is a reasonable value. But this value of permeability is averaged over the entire area of ice. So it may come due to the some channels, but in most of the region permeability probably is lower. So then we have, of course, some small delay, but amplitude of water level inside cofferdam is almost the same as outside. So then, that is what we observe. So then, filtration velocity about 0.1 millimeter per second. So then I calculated flood time as a function of tidal amplitude. So that's for different values of tuning parameters. So then it gives some reasonable agreement with this blue point where calculated using image of time lapse camera. So then water level and flood time relatively the ice is in model it up to half of meter, but we need to count that of course it is not flat real surface, but it is like that. So therefore we may have mean level 10 centimeters, but in deep part we may get it deeper. So then next we want to model temperature inside. Temperature inside ice is key parameter for the calculation of thermal expansion. So then we use for that equation of heat transfer, and in this equation we substitute this heat advection with filtration velocity, which is not exactly filtration velocity which was reproduced with Darcy model, but we have some coefficient alpha f, because as I mentioned we may have channels, and these channels don't have influence on the temperature in the ice body. They have only local influence. So then we also include into the consideration the dependence of specific heat capacity from the temperature. It is quite strong. So that is known effect. So then in addition we took into account this salinity profile, which is changing from this value from 5 to 2 at the surface to this value in high tide. So then actually temperature profile is like that, but this boundary is moving up and down with semi-diurnal frequency. And we, in boundary condition, we keep temperature at the bottom minus 1.9 and at the surface minus 10, assuming that that is constant air temperature. And with these parameters, we have mean temperature profile, which is changing over tidal cycle, but it looks similar to natural, but we need to use coefficient 0.1. So then it means that 90% of water on the ice surface appear due to the migration through some channels, but the rest of water, 10%, only move through the ice body and influence temperature change inside ice. So then here is temperature variation. They look similar to measured temperature variation with maybe change about 1 Kelvin. So then if we would assume that all water migrates through the ice, so then we would have this picture. Very strong temperature variation. But anyway, these temperature variations observed and modeled can be explained only by periodical migration of brine through the entire ice column. So then about stresses inside ice. So then I use again this equation, but then I need to substitute. I use dimensionless variables, and I have coefficient of thermal expansion nu, and I substitute that is some constant multiplied on coefficient of thermal expansion for fresh ice. It is 5.5 times 10 in minus fifth Kelvin. So then this is linear coefficient of thermal expansion. So then I use representative values for this constant, and 1 gigapascal, 2 gigapascal for elastic modulus. So then these two coefficients, they are 14 and 0.1. So then it is 0.1, that is 14. So then if stresses are low, so then creep is not important. If stresses are high, so then creep important. If we have a coefficient of thermal expansion for fresh ice and temperature variation 1 Celsius degree, alpha T is temperature amplitude, so then the creep is not important. But so, and we have this is tide, and blue curve show oscillation of pressure inside ice with amplitude 0.1 megapascal. That is close to observed, but maximal value were close to 0.5. So then, and they were observed 2013 with some phase shift. So then I got this value when coefficient of thermal expansion is negative, when we have this this term equal to -10. So then coefficient of thermal expansion can be negative, and then we are going back to the experiment of Malmgren. He published it 1927, but he performed experiment on board of Mott together with Amundsen. So he measured it in experiment coefficient of thermal expansion, and this point shows that when temperature range is relatively high, so for normal salinities of ice, so then thermal expansion is negative and coefficient is quite big. It is 100 times bigger. So, and this is a density of dependence of sea ice density from the temperature for different values of ice salinity, and that's air bubble content. So this formula from paper of Schwertfeger. And these lines are calculated just using this definition of the coefficient of thermal expansion using the density from Schwertfeger. So, but the point is that if ice is permeable, we cannot assume that mass is constant, and this definition is not valid anymore. So then at this point I want to show you three sentences from different papers. So Gordon Cox, 1983, published that coefficient of thermal expansion natric chloride ice and natural sea ice is the same as that of pure ice, because in saline ice the matrix of pure ice expands and contracts without regard to the localized phase change in the brine cavities. So then he said that Malmgren experiment was not correct, because Malmgren placed a piece of ice in an iron tube, and he changed temperature and observed change of petrol level around the piece of ice. He placed petrol. So, and he observed change of petrol level, and based on that measurements concluded about negative expansion. But Cox said that it's not correct, because that was not real expansion of ice, but he measured change of level because of brine movements from the ice and into the ice. So, and later 1990 it was confirmed by Johnson and Menzner. They published the result of experiments, and I think that they mentioned their call in acknowledgements. So they use very small ice piece from landfast ice on Alaska, and they measured positive coefficient of thermal expansion, but not the same as for fresh ice. But their conclusion was that that was mistake of experiment, but coefficient of thermal expansion the same as for fresh ice, in saline ice. But then Wicks and Eckley, they said that columnar sea ice is impermeable to brine transport when the porosity is less than 5%, and salinity is less than 5 ppt, what is quite typical. So if ice is not permeable, so that's evident that there is contradiction between these statements. So then later Ken Golden together with colleagues performed experiment about conductivity of brine cells in the ice, and they also supported statement of Wicks and Eckley that when temperature is low, there are a lot of brine pockets which are not connected with each other, and when temperature is bigger, then they became connected. So, and I was thinking that maybe main point is the size of spacemen. So therefore, we were searching for some equipment how to measure thermal expansion of bigger ice spacemen, and we stopped. We were happy with these fiber optic sensors, which are fixed on the spacemen, and they measure with high frequency deformation and temperature inside. So this is temperature sensor. Then we place around plastic vessel to avoid evaporation. So experiments were running over over the many days. So, and we got that if ice is salt enough, so then we may have a negative thermal expansion. When ice is 2.3 ppt, it is positive, but not the same as for fresh. And then we got 2 points from Johnson and Menzner paper for the same salinity. So they just fit very well our measurements. So therefore, there is reason that coefficient of thermal expansion could be negative inside Cofferdam. And finally, I would like to formulate a reason for that. And here you see experiment performed in Svalbard last winter. So we use this device producing compression of ice over entire ice thickness. And we applied pressure around half of megapascal and then drill not through holes in front of this plate. And observed that water didn't penetrate in holes here, almost at all. So then compression, so this we place at the bottom of each cell pressure sensor, and it also measured temperature. So then in an extended hole from the plate, where ice had small compression, the water came through the ice bottom very quick. And in the hole just near indentation plate, the water penetrates very, very slowly, and in other places it didn't penetrate at all. So then this compression destroys system of channels in ice, and brine cannot penetrate through the ice. And this ice may have negative thermal expansion. So then I have 2 pages of conclusions, just where I just want to repeat what we did. Confined ice frozen to Cofferdam walls is formed below the cold quay Kapp Amsterdam. The ice thickness 1.53 meters inside the Cofferdam, and it is much higher than ice thickness in the fjord. Seawater flood is observed on the ice surface inside the Cofferdam, and measured depth of flood water reach 20 centimeters. Ice pressure up to half megapascal were recorded on the Cofferdam walls in 2 winters, over 2 winters. And highest pressures were registered when on the walls where we having maximal deformations, and when temperature was above -10. So registered pressures oscillate with semi-diurnal period and reach maximal values where tide amplitude is maximal in spring tide. Ice temperature measured through the entire ice thickness inside the Cofferdam oscillate around mean profile. Surface temperature follows the air temperature. Temperature at the bottom equal to the water temperature. Semi-diurnal oscillations of temperature are most visible in the middle part of the ice, and their amplitude vary from some tenths of Kelvin degree to 2-4 Kelvin, depending on the place inside the Cofferdam. Semi-diurnal oscillation of ice temperature follows the tide. The temperature increases with increase of the sea level. Highest ice pressure is mostly observed in high water time with highest ice temperature. Phase shift of highest ice pressure with respect to highest ice temperature up to 6 hours were observed in 2013. Water migration through solid ice was observed in laboratory conditions. So, and mean filtration velocity of brine through the ice in Kapp Amsterdam was estimated below 0.1 millimeter per second, and mean ice permeability is about 10 in -10. Semi-diurnal oscillations are reproduced with heat transfer equation, where we substitute filtration velocity 1/10 of mean filtration velocity over the entire ice thickness. Heat transfer equation takes into account the heat advection due to the brine migration and time-dependent profile of ice salinity. Amplitudes of measured ice pressures are well modeled by the rheological equation describing a balance between thermal strains, elastic stress, and viscous stress. Observed shift of several hours between maximum of temperature and maximum of ice pressure are calculated with negative coefficient of thermal expansion. Negative coefficient of thermal expansion is related with low permeability of compressed ice. Effect of strong decrease of ice permeability was discovered in field tests performed on compressed sea ice. So, of course, the help of UNIS logistic for installation of these sensors and thermistor string on the quay is very important. And the work was supported by project SAMCOT. And here you see current situation. Actually, these workers in coal company, they weld. This distance is growing from year to year, and they weld thicker and thicker plates here. But now coal company finished activity in Svalbard, so we have good site for observations. Yeah.
Any questions, please? We have almost 15 minutes before reception.
A very nice presentation. I was just wondering the amount of pressure that you would get built up as I guess when you have tidal rise and you have landfast ice that's connected. Presumably you'll have deformation that's greater as you get further from the shoreline, but near, where it's close to the connection point on the shore, presumably you would have. I mean, would you expect to have accelerated sort of brine migration processes in areas where you're in very shallow water, where you're going to get localized pressure accumulation?
Yeah. So then even what we did, we have very shallow water in Svea, but not near quay, but deeper in fjord. It is very shallow water, and there is ice and snow on ice surface, and snow thickness is could be up to 1 meter. So then I place salinity sensors star ODI on the surface of ice between snow and ice, and I measure it salinity over the tidal cycle. So then on certain stage water penetrates through the ice and we registered salinity.
And so you get flooding of the snow up, and the flooding level increases over time as so even though near shore where it's attached, presumably it wouldn't rise and fall as much, but I guess and does that extend quite far out as well?
But in the end of fjord we have some rivers coming from valley, so therefore this river body, it is ice is sitting at the bottom but partially floating along rivers. So, and in that place we observe this flooding, so then systematically, yes.
And do you have any idea of how much relative flooding would be through cracks in the ice as opposed to, would you get enough pressure to force the water up through the brine?
But we made it in ice tank. In ice tank we had the pressure maybe 10-20 centimeters over pressure. 10-20 centimeters was enough to press water through the ice with thickness 10 centimeters and cold ice with -10 at the surface. And of course some part is going through the crack, but inside the quay crack are not visible. The ice is quite thick, and when I tell about this ice, landfast ice, so then that's about 1 meter thick, but here it is 2 meters thick. That's quite.
Yes, question. Aleksey, thank you very much. Very interesting features are covered. One question, possibly concerning to global ice dynamics in seas. We are partly involved in possible modeling. When you said that possibly saline ice has a negative coefficient of thermal expansion, could this influence on ridging appearance in ice floors in the sea? Because in rivers we know the decreasing temperature originates the cracks, so ice is shrinking, but maybe in seas with saline ice we have some contraction, and this could initiate the ridges appearance.
I think that there is some critical value of compression which is able to destroy porous space.
And what gives your...
we don't know. We only performed the first set of experiment, and we want to repeat that. And also I think that the capacity for permeability will be reconstructed after the compression, not immediately. It will take some time to get an initial state. At least after this experiment, we repeated the same experiment with lot cells frozen in the ice, and we compressed ice and then dropped the lot. And it was very long time of relaxation for the lot cells frozen just in places with maximal compression.
Is it right that the water which comes from the surface from below, it's with a higher salinity than the average water?
Of course, because everything in equilibrium with air temperature. And in laboratory conditions, when we have ice tank, so then ice is frozen to the walls. And when the air temperature is low, ice is growing downward and increase pressure inside the water. Therefore, we always have some liquid film on the surface of ice, even if we have -20. But then we have 100 ppt salinity. We have very high salinity on the surface. Yes,
so it's not frozen, or it's frozen but very slow?
It is not frozen because has very high salinity.
Any more questions, or either we go for reception? Thank you very much for all speakers.